going to talk by Michał Rams, who is our speaker today. The smoothness of the invariant measure for random iterated function systems. The floor is yours.
Thank you. Okay. So I will be speaking today about something that we did with Balazs, because I just spent 4 months and a half in Budapest, and we were doing different things. And this is a paper in which we were used the tools that were Newton, that is some probability theory and some Fourier transforms. And as the result, I had several great surprises, that these things turned out to be completely different than I thought. I mean, it means that I should read some textbook, I guess. So I had some discoveries that are probably obvious to anybody who has any idea in these areas, but still I will share them with you so that you can have a good laugh at my cost. Anyway, so what we are going to do, we are going to look at the linear iterated function systems on the line. With this we have some finite collection of maps of that form, and we are mostly interested in the limit set, which is the unique non-empty compact set satisfying the following equation. Okay, then this is long known, so let S be something which we call similarity dimension, that this is the solution of the equation the sum of lambda I to the power S equals 1, and then there are 2 cases, that is if S is smaller than 1, then generically the Hausdorff dimension of lambda equals S, generically meaning for almost all choice of translation, that is, we fix lambda i's and we are varying t i's. And if we have S greater than 1, then again generically we have Hausdorff dimension of the limit set to be 1. Moreover, we know that the Lebesgue measure of the attractor is positive, and moreover we know that the natural measure is absolutely continuous with respect to Lebesgue and its density is square integral. Okay, what is this natural measure? Okay, so we need to define first the symbolic space. The symbolic space is simply the set of all possible sequences of symbols from 1 to k. Each symbol corresponds to one of the maps that we are using.
Excuse me, do you need any kind of open set condition or something like that?
No. This genericity is this. If we have open set condition, then we simply have this formula. So if we have the open set condition, we automatically know that S is not greater than 1. This kind of results, okay, it goes from 85, from Pollicott and Szymon, then Perez, Szymon, Sołomek, and so on. There is a long string of results, but the assertions are basically the same, that the improvement goes in the direction of improving the statement of generically. That is to say that the set of exceptional parameters is smaller and smaller. But the positive assertion is constantly this. Okay, when we have the symbolic space, we have the projection.
Is it possible it's always true, or you have?
No, it is not always true. We have counterexamples. Well, if all the ti's are equal to 0, then all the maps have common fixed point at 0. Then the limit set is simply this fixed point at 0. And of course, how the dimension is 0.
So when you say it's improving, that is not that there is like a conjecture optimal statement.
That is that long-term conjecture is that there are only countably many. That is that the only possible counterexample is when those ti's are in such a form that you have exact overlaps of some branches of the iteration of the maps. Then is the general formula of the projection map from the symbolic space into the attractor. This formula is simply working in general for any iterated function system given by some finitely many contracted maps. But in case of linear maps on the line, this formula actually, this can be written as in the formula. We can write it like this. That is when we are iterating the maps like this, and this iteration is going to be by multiplying everything we had up to this time by corresponding lambda and adding this constant. So we start from the last, so when we look at this object, and we will start from t omega 1 plus lambda omega 1 t omega 2 plus lambda omega 1 lambda omega 2 t omega 3 plus. And this is exactly what it is. This notation is for the product. Okay, so this is the type of system that people are studying for more than 30 years. Plenty of things are known. Okay, but what I'm going to speak about today is...
Excuse me, I'm a bit confused about the formula. You don't need to take any limits on the right hand side when you take summation?
Well, the sum goes to infinity.
Ah, okay.
Okay, what we were doing with Balazs is the randomized version of this. You can randomize it in many different ways, and we were doing this in the simplest possible. That is, we were adding some random translation at every step. And to make things, okay, now you can do this random translation again in different ways, but we simply assume that we have the formula by theta of omega. Theta will mean the dependence on the probabilistic parameter is going to be equal the sum from n1 from infinity lambda omega n minus 1 times t omega n plus theta omega n, where this theta omega n is this random translation that we are adding. That is, to theta omega n are independent, identically distributed random variables. Strictly speaking, we don't need identically distributed, but I'm taking the simplest possible case. Which have the distribution of theta. Every random thing in the paper we are calling theta.
Excuse me, Michał, I think that the T omega sub n, not super n, T omega sub n, not,
You are right.
thank you.
And for theta, you still have omega superscript?
Yes, yes.
Ah.
That is, when you look at the symbolic space, you can think of this as of a tree of all the possible choices of symbolic sequences, and at each node of this tree, at each vertex of this tree, you choose independently the translation. Okay, so it's object like this. So because this is random, then we are going to ask questions. Oh my, I've forgotten. I talked about this projection, but I still haven't told you what is the nature measure. The nature measure is simply the projection under this projection pi of the measure nu, which is the Bernoulli measure on the symbolic space. Given by the probabilistic vector lambda 1 to power s, lambda k to power s.
But is it also physical?
I don't understand the question. This is the measure which is living on the attractor.
I know, but is it true that if we start with the basin
Yes.
using the Lebesgue measure,
I think so.
Look,
like in SRB,
we've got a dynamical system here. We have several maps. If you start from any point and apply those maps at random with this probabilistic vector, then the weak star limit of your trajectory, the Berkov limit of your trajectory is going to be this measure, yes.
But with respect to one measure, because you don't start with that value.
If you start at any point, the limit, the maximum contraction, so the limit measure does not depend on the point that you start from.
So it's kind of starting from a point measure.
It was, you can start not from the point, but you can start from any measure, you will convert the same thing. This is simply contracting operator.
And when you say random, which you mean random according to the rule of the IQ.
Okay. Why this measure is interesting? Well, in case you have open set condition, this is going to be the measure giving the maximal Hausdorff dimension. In fact, this is going to be the Hausdorff measure in dimension S. In this situation. Okay. So coming back to the random. So in the random situation, we have two expectations. One expectation is that the randomness, so when we are looking at the random process, we are automatically only asking about what happens generically, is what happens almost surely. So the, one expectation is that this randomness is going to replace this generic assumptions of the deterministic situation. That is, we expect the same results which are generic in the deterministic system, we expect them to be almost surely obtained for the random system. And second thing is that what we expect is that the randomness is even slightly better than the generic situation, the deterministic system, because in the deterministic system, the situation is that if you have those maps somehow badly arranged, I don't want to say what does it mean badly arranged, but they are somehow in bad configuration. Those translations are not good for us. Then this bad situation is going to be repeated on every scale. Meanwhile, in the random situation, even if at some scale the random things were arranged badly, this does not say that this will be repeated on the next iteration. So random is somehow nicer, and we normally expect that we can get slightly more. Okay, and what happens is exactly what I'm saying. That is, there is the paper by Brownian, Pollicott, and Smoothness, which says that almost surely, for the random system like this, we have the same things that we have there. That is, if x is smaller than 1, then how the dimension of the attractor is equal to s, and if s is larger than 1, then the measure, then the natural measure is the projection of this Bernoulli measure from the symbolic space under this random projection. It's absolutely continuous with respect to Lebesgue, and it has L2 density. But we get something more, and we get the result by Dekking, Szymon, who was it, Szekeres? Szekely. which says something more, that is, it says that almost surely, if S is larger than 1, then that has positive Lebesgue measure. Okay? And what we
I'm sorry, Michał.
Yeah.
I'm sorry. We proved that the interior is non-empty.
sorry. Yes, yes. Yeah, sorry. Yes, that's what I wanted to say. No, the positive Lebesgue measure is, I think, Jordan Pollicott. This result says that actually the limit set contains an open ball. Almost true. Okay, so it is a very nice constructive, in a sense, proof. Okay, so what we are going to do with Balazs, or rather what we did with Balazs, is that almost surely, if S is larger than 1, then mu theta is the density of this measure mu theta, that we know already it is L2, it is actually Hilbert continuous. And of course, this actually implies that the attractor contains an open interval. However, this statement needs some minor assumption about the translation. It's not enough to say that the translation is absolutely continuous with respect to Lebesgue. We need some special assumptions. And the proof is totally non-constructive, as you will see now. Okay, so. So, how are we going to prove it? And okay, we are being inspired by a paper by Erraoui and Hakiki. Probably I'm spelling them very badly. Those guys are doing something for the fractional Brownian motions. But they used a method, and we decided with Balazs to check if maybe this method is useful for us, and it turned out that it indeed is. So what are we going to do? There are two main parts. The first part is that we are going to use something called Kolmogorov continuity theorem. And the probability theorem. What is this theorem? Well, even if you know about probability as few as I, even then you know that Brownian motion is the stochastic process in which almost every trajectory is continuous, almost sure. Which is very interesting because, after all, Brownian motions is not defined in terms of trajectories. It is defined in terms of distributions and in terms of increments, that is the differences of distributions at time t1 and t2. There is nothing about the trajectories, but Kolmogorov continuity theorem is exactly the tool which lets you prove that the stochastic process has continuous, even Helder continuous trajectories if you know something about the distributions of the, well, about the increments of the random process. That is what it says, and I am lying here a little bit, in fact more than a little bit. For the random process, we write the expected value of x of t1 minus x of t2 to some power p. And if we know that this is larger than some constant times t1 minus t2 some power alpha, where alpha is larger than 1, then this implies that the trajectory is almost surely Helder continuous. Almost every trajectory is Helder continuous with exponent alpha minus 1 over t.
Sorry, Michał, in the assumption, do you want a lower bound or the upper bound on the expectation?
Upper bound, of course. I'm sorry.
Thanks.
I'm sorry. Okay. Now, this is not true what I wrote. And what is not true in what I wrote, I will explain you later. Okay, but this is what we are trying to check. Okay, how are we going to apply it? We are going to write the density of the measure mu theta. That will be known by v theta.
I got lost, I didn't follow. You assume expected value is.
This is the assumption.
And then this is for typical trajectory?
Almost every trajectory is.
Almost every. Less than continuous, but still almost.
Well, it's better than continuous. It is even Helder continuous.
Even, but this almost every might be
Almost every.
smaller, maybe smaller almost every.
I don't understand what is smaller almost every.
Prawie wszystkie, może być też prawie wszystko, ale nie.
I don't understand this. Simply, if we have this assumption, then the event that the trajectory is Helder continuous with this exponent, or more precisely with every exponent smaller than alpha minus 1 over t, is almost sure.
Almost sure.
It's measurable and of probability
Set
1.
of full measure, but
Yes.
maybe smaller than the previous set of.
Yes, no, I don't know. This, we are only talking about almost sure. Yes, so
Yeah, that was the question.
I don't know which
You
of
don't
the.
care now what does it mean.
No. Okay, so coming back. We have the density of mu theta, and we denote it as v theta at some point x. And we are going to treat this as the random process with x being the time. As we are doing the random process somehow sideways. And we want to write the expected value of v theta of x1 minus v theta of x2 to some power t. And if we are able somehow to prove that this is smaller than c1 minus x2 to power alpha for every x1, x2, and for some alpha larger than 1, then we are going to apply the Kolmogorov theorem and say, okay, so this means that the trajectories of this random system, and those trajectories are simply functions of density of our limit measures, are Hölder continuous. Okay. Now the question is, how are we going to calculate something like this? Yeah, because when we look at the formula for the, well, it's not clear how to calculate the density of such measure. So we have some symbolic space. On the symbolic space we have some Bernoulli measure. We have some projection, some random projection defined by some formula. And, well, even the fact that this projected measure is absolutely continuous is already quite interesting. But how are we going to write the formula for the density of this measure?
And this was not used before, right? It's part of your result.
No, this is from Pollicott Schumann.
Ah, it was new.
This was not. We are not proving this, we are just bootstrapping ourselves from the knowledge that it is absolutely continuous and has L2 density. But still how to write the formula for this? Well, it's not clear. However, let's look at this formula. What we see here is actually concatenation of measures. And if it is concatenation of independent measures, then it is reasonably simple to calculate the Fourier transform of this. It will be simply the product of Fourier transforms.
Coordination, you mean convolution or?
Convolution. Sorry. I'm sorry, my brain is not working as it used to do. If it used to do. Whatever. With the convolution of measure, you can calculate the Fourier transform. And as we know that the measure is L2 almost surely, then the Fourier transform is also going to be L2. And then how do we get the density? Well, by taking the inverse Fourier transform. So the part 2 is calculate v theta hat and then apply the inverse Fourier transform. Okay, and what we will have the Fourier transform of this, it will be some very ugly infinite product of Fourier transforms. Then we apply the inverse Fourier transform, which means we add one more integral in the very beginning. And then we will do what? We will, well, change the order of integration, and we will do some Houdini magic, and we will hope for the best. Okay, now, that's the plan, and of course, no plan survives contact with reality. And there are things that, I don't know, Balazs probably knew them, but for me they were complete surprise. So, the first thing, how are we going to calculate the inverse Fourier transform? Of course, books tell us that if we have the function which is in L2, then we can calculate the Fourier transform or inverse Fourier transform. Well, the books are lying. You can calculate Fourier transform if your function is L1. When the function is L2, you cannot calculate Fourier transform, period. So what is this L2 thing that people are talking about? Well, you can do the following procedure. You have some L2 function. You can take another function which is both in L2 and in L1. For example, you take your function and you restrict it to some bounded domain. Yes, it will be L1. Then to this function you can, for this function you can calculate Fourier transform. Then you can take the sequence of functions which are in L1 intersected with L2, which converge to your function. Now, for example, take larger and larger bounded domains. And you can calculate the Fourier transform for each of them. And then you can take the limit of those Fourier transforms. It turns out that this limit is very nice, behaves very nicely.
Because it's an isometry.
Because it's isometry, yes. And so you can, what you obtain is some operator from Hilbert space to Hilbert space, and you call this operator Fourier transform to confuse everybody. But the limit in which you have this convergence here is not pointwise limit, it's L2 limit. And this means that you have an abstract operator, but you do not have any integral formula. You cannot write this Fourier transform that you just defined as integral of e to power minus I x psi yada yada. All this doesn't work. And, well, there is no way around it, because this means that to calculate the inverse Fourier transform, we would have to know that the Fourier transform of our strange measure is in L1, and we have no way to check something like this. So basically it means that we can do nothing, except in dimension 1.
But why can't you take approximation, like in definition?
Because we do not have pointwise convergence. And this means that the limit of the is what you want to have is pointwise convergence of those Fourier transforms. And we don't have it. Except in dimension 1. There is a theorem by Carlson in dimension 1 which gives us the pointwise convergence. So it's not too...
If you don't have pointwise convergence, then you don't have a hope to obtain in the limit some reasonable inequality.
Yes, that is then, if we do not have pointwise convergence, we do not have any integral formula.
If on the left-hand side you have an integral and you have an expectation, so I think you cannot rule out that this is well defined in some sense.
Yes, but we cannot calculate anything, okay? calculate anything, we need to know that we have the formula for the Fourier transform. I mean, for the inverse Fourier transform.
So to understand correctly, that you just will not be able to obtain this formula E with theta x1 minus with theta x2 inequality. This because you don't know actually the values at points. You
Yes.
know only function up to some L2 small L2 addition.
Yes.
I see.
Let me keep this formula still on the blackboard. Theorem. Theorem is as follows. If S is L2, then
It's only clear points
on the line.
on the line.
This theorem is only on the line. Then for almost every x, we have f of x equals limit n going to infinity, and then 1 over 2 pi integral from minus n to n e to power minus I x f hat x dx. And this theorem is working only in dimension 1. In higher dimension, there are counterexamples.
Is it important you have a symmetric segment? Can you take integral from minus n to 2n or something?
I think you can play with this. Yes.
Całka niewłaściwa.
Okay, so this is, of course, it gives us some headache, the things are only defined almost everywhere, not at every point, but that's maybe not a problem because we are anyway talking about the density. I think density is defined almost everywhere, we don't care what happens on certain measure 0. The greater problem is, of course, that this is only in dimension 1, and this is why our result is only working in dimension 1. Everything else could work in any dimension, but we just aren't able to calculate the inverse Fourier transform in any dimension larger than 1. Okay, and that was the first figure. Okay, but now, okay, we can calculate the Fourier transform, we can calculate the inverse Fourier transform of the Fourier transform, and let's say we can calculate this expectation. This will be some very nice big integral. Okay, and we get this explanation. So are we then happy? Can we apply the Kolmogorov's theorem? Well, answer is no. Answer is no, because the Kolmogorov theorem doesn't say what I told you. It cannot tell something like this, because this is mathematical nonsense, what I wrote. You see, random variable is not a function from some probabilistic space into, say, real line. It's a real valued random variable. Random variable is the equivalence class of such functions, where we identify functions which differ at set of measure 0. And random process is, again, not a function from probabilistic space times parameter space times space into the real line. It's, again, an equivalent class. And the property of having continuous paths is not an invariant of this equivalence relation. So it is, while the assumptions here, they are the same for every element in this equivalence classes. If we take the two random processes, but we change them on the set of measures 0, then it changes nothing in this assumption. So the answer is not that the Kolmogorov theorem doesn't tell us that X has continuous trajectory. It tells us that there exists another realization of the same random process, and this other realization will have continuous paths. So, what this will give us? So it will not tell us that the function mu theta of x is Hölder continuous. It will tell us that there exists some function g theta of x, which is which passes Hölder continuous, and such that for every x, g theta of x equals b theta of x almost surely. Okay? And of course, what we want to say, okay, so because of this, it means that actually g theta also has continuous trajectories almost surely. Yes, it would be the standard Fubini argument that the set on which they differ is measure 0 on every vertical, so it is. But then there is another thing that was a big surprise to me. That is, okay, Fubini theorem has assumption. Assumption is that the function is measurable. The function here being the difference between g and v. V is measurable function. G is random process. But G being random process does not imply that G is measurable. Again, for the same reason. Being measurable is not an invariant of this equivalence relation. You can easily find realization of the random process, which is, of course, measurable at every time, and it can even have every path measurable, but as the function of two variables, it is not going to be measurable. So, a priori, we don't know that G is measurable. I mean that I learned probability theory some 30 years ago, and all this time I had no idea that stochastic processes are not measurable. Okay, so what we can do? Well, we can do two things. One thing we could do is, okay, this G is not any realization of the random process. It is the realization that is given to us by the Kolmogorov continuity theorem. So we can simply go through the proof of the Kolmogorov continuity theorem. This proof is constructive, and we can check whether this object that is being constructed there is measurable or not. Okay, but we did something else. We made a lemma which basically tells you that if you have the random process which trajectories are continuous, then this random process is automatically measurable as the function of two variables. This, if we have some function we have two compact sets, and if our assumptions are that for nu almost every y, the function is continuous, and second, that there exists a dense.
By the function is continuous, you mean that
Continuous
in the class
for
of
fixed y as the function of the variable x.
but for fixed y still it's a class of function at all two or
No, at the moment I'm simply talking about functions.
Oh, functions. Okay, no.
We have one function. The first assumption is that almost all horizontal leaves are continuous. The second assumption is that there exists a dense subset of x, such that for every x in x prime, the function f of x dot is measurable. If we have those things, then f is measurable. So, if you are doing some second calculus classes and you need some problem for students, okay. This basically tells us that this function g here is measurable, and so we can apply the Fubini argument, and we get that this will imply that indeed the function v theta is almost surely Helder continuous, and that's what we wanted to obtain. And I mean, there is one more tiny problem. The tiny problem is that this Carlson theorem only gives us this formula almost everywhere, not everywhere. So this means also that in this Kolmogorov theorem, we will have actually the random process for the time not forming an interval, but just being some bounded set of reals. But that's not a problem. There are versions of Kolmogorov continuity theorem which are doing like this. We don't need time to be the whole interval. And second thing, of course, that when we have continuous function which is defined on some full measure set, this does not mean that you can expand it as the continuous function to the closure. But the good thing is that we are proving Helder continuity, and when we have Helder continuous function, it can be expanded to the closure. everything works. Everything works, and the only thing that we still need to do is not those ugly measurability stuff, but the nice thing that is quintuple integrals.
What?
Quintuple integrals. And this will be a lot of calculation, which I will better write.
Can you repeat the assumption on the function of the random perturbation, right? Because you need.
I haven't told you what the assumption is. The assumption on
You
this,
haven't told us?
no,
But because aren't you supposed to verify the continuity, the first continuity in the lemma? How do you verify the first
this,
condition? Yes.
well, this is automatically verified because I want to apply to something which is given to me by the Kolmogorov continuity theorem. So, Kolmogorov continuity theorem is giving me the random process such that almost every of its trajectories is Halder continuous. What I don't know is whether this random process is a measurable function.
You mean the second thing?
Oh, the second condition is simply that it is random process. That is, what we see on those sections are the random variables. Random variables are measurable by definition. They have to be.
Who are x and who is y?
X is X. Y is the probabilistic space. This is what I denote by theta here. And so the first statement tells me that almost every path is continuous. The second statement tells me that at least on a dense set of times, what I see is the random variable, self-measuring. I mean, of course, this thing being random process means that at every vertical section, what I see is something measurable, but the proof only needs countable dense subset, so that's how we formulate it.
I got a bit confused. How do we get random process? Because to me it seems that like we have sequence theta, omega, n of random variables.
Well, the random process means, well, the type of this random process is the position. It's at every x on the, we have the measure, for example, distributed on some interval. At every point of this interval, we have the density of the measure, and the density is random object, because the measure is random. And then it is parameterized by the position, which plays the role of time in this random process. So at every x, we have the separate random variable, and when we are changing x, this constructs the stochastic process. It is, well, sideways. Okay.
Excuse me, Michal. Excuse me. So you say theta is equal to y. So on the other blackboard, which is further away, y is actually not the real line.
Yes, that is this x and y are here simply some compact measurable spaces.
Yeah. That's so it is not okay. Thank you. X is the real line and it is the time, and Y is this theta basically. Thank you.
Yeah, matrix possible. Okay, so first, let's start from writing. This is the object that we will be using, and important thing is that this is real valued function. It is real valued function because we have the symmetric bounds of the integration. Okay. Now, what we are trying to calculate is something that we know set of AB, which is the integral of b theta of A minus b theta of B taken to some power P dp of theta. This is, and what is P? I don't tell you yet what is P. The only thing I want at the moment is that P is even. I want this to be even so that the function here is non-negative. Because I want to estimate it from above, and it is simpler to estimate from above something that is non-negative. Okay. So what is this? This is one of the integral. Limit of n going to infinity. F. Without this one, but it doesn't matter. This is constant anyway. F of n minus f n d theta to power p. dp of theta. Okay, now if when we are looking at this function at different x and what is changing, this part is not changing. The only thing that is changing is this part. Okay. Okay. This is Fatulema. Yes, we can put this limit outside of the integral. Okay, and what do we have here? Then we have integral from almost n to n. Product from 1 p e to power minus r a xk minus e to power minus r b xk times the hat of x1 with the hat of xp x1 xp dp of theta. And that is each of those guys in this product I'm writing as an integral. So this will be the product of p integrals.
So inside the brackets raised to power p, you have absolute value of difference? Or
No, they are real numbers, and I'm taking them to the even power.
also p is okay.
That's exactly why we want p to be even, because if we had to put absolute values right here, then things would not work in what follows. But we will put absolute values in some time in the future, but not yet. Okay. Okay. I think this is the moment where we can pass n to infinity. No, we first need to put absolute values. And well, okay, we put absolute values, we applied Fubini theorem. Now everything here is positive. We can get rid of the limit. So pass with n to infinity. Okay. I will still need this one. Not yet destroyed. How are we going to estimate this thing? Well, we are going to say that absolute value of e to power minus I eta minus 1 is smaller than c eta power gamma. This we can do for any positive gamma, and we will do it for some small gamma which later. So what we have here, we have some constant, okay, times a minus b to power p gamma. And this is what comes from applying this inequality p times. And then we have integral of absolute value of Szekely power gamma times times integral b half of okay. So now we want to take a look at this thing. And now we will finally substitute what are those b that are this thing equals absolute value of the integral. So let's take 1, 2 e to power I Szekely and theta of omega. Okay. Something like this. That is this object. Well, we have the Bernoulli measure on the symbolic space. In the symbolic space, we have p points, and we project those p points by this random projection by theta. Okay, so putting what is this pi theta? It is here. Putting absolute values inside, what we have okay, let's keep it outside. E to power I sum from n equal 1 to infinity lambda omega n minus 1 depends on k and I will keep theta. Okay. Now, the part with translation doesn't matter. This is simply multiplying the function by something of absolute value 1. The important part is this thing. So, what do we have here?
Excuse me, it's time to understand better what's going on. So we set theta for each theta is a map, right? From omegas to real numbers.
Theta omega n are IIT. Actually, they don't have to be IIT, they have to be independent, and we need to have some common boundary distribution. But let's say they are IIT of some random variable theta.
I see. And now you're taking Fourier transform of this map. What is that?
Yes, that is, I'm taking this. Yeah, this is Fourier transform of a measure. This measure is obtained as the projection of the Bernoulli measure on the
I see, yeah.
symbolic space and then the map by theta. What I'm getting is exactly this one.
Yeah.
Okay, and now what we do, now we want to write this in the terms of Fourier transform of theta. Because you see, all those objects here are like Fourier transforms of the same random variable, of the same distribution theta. It's just that because it's a convolution of copies of the random variable theta, only translated and displayed. So this thing will be infinite product of the Fourier transforms of this theta, only again rescaled and multiplied by itself. So what we can write is that for a given, if we denote this by W, then W of C1, or maybe of omega 1 up to omega T, it is what? It will be the product of omega 1 to infinity, product for all words of length m, theta hat of lambda tau n-1 times this. And here there is something strange. Something like this. What is this? That is when we are looking at, okay, what we have in this product is that we have P words, P infinite sequences, omega 1 to omega P. And each of those for each of those sequences, we have such infinite product which contains one element corresponding to the first symbol, one element corresponding to the first two symbols, one element corresponding to the first three symbols, and so on. So at each number of symbols, we have exactly p elements in this product. And these elements coming from the sequence omega 1 are coming here with the variable xi1. Those coming from the sequence omega 2 are coming here with the variable xi2 and so on. Okay. Of course, some of those words can be repeated. As p might be larger than the number of symbols, so for sure there will be two guys that have the same first symbol, for example. And then this will be repeated for both. Okay, so when we replace this by the Fourier transform of theta, and inside theta we will have something that we take the product from, for every possible length of word, the product over all possible words of this length, Fourier transform of theta at, so this is the constant that you have here, the normalization constant, which goes to 0 very fast, which is a problem, multiplied by the summing of those random variables for which this word appears. The sum might be 0, as there are just p different, just p words that in which something non-zero appears. In each element here, xi1 will appear for exactly 1 tau n. This tau n which is equal omega 1n. xi2 will appear for exactly 1 tau n. xi3 will appear for exactly 1 tau n. Okay, so we have such function. Now I can tell you what is our assumption about theta. Our assumption about theta is the absolute value of theta of x is smaller than 1 over 1 plus x power n where n is larger than s. Why do I need this? I need this to be able to integrate those things. Yeah, but observe that because we have those numbers lambda tau n minus 1, those numbers are smaller than 1. So they are, we have the fast decaying function, but those things are exploding us. That's the function that we have in this product are less and less slowly decaying. The good thing is that all those functions are smaller than 1. The absolute value of the Fourier transform is smaller than 1. So this means that we can actually get rid of some of those functions if we want. We have infinitely many, maybe we don't need them. And that's what we will do. How are we going to do this? We will just choose p of those words tau n. And we will only take the Fourier transform corresponding to those p words. And we will have the product of these p functions, and we will integrate this product in the p-dimensional space. So, and those functions will be of the form function, which will, with such a decay, of some vector. The domain here will be some certain sum of xi's. So how do we calculate the integral or something like this, well, we will change the variables. So we make those sum of xi to be the coordinates. So what will appear in our calculation will be the inverse of the Jacobian of this transformation. Now, of course, this will be the integer valued matrix, so the Jacobian cannot be smaller than 1, except if the Jacobian is 0. This we need to know that those p vectors that we will choose are independent. So what we will do? Once again, we have the symbolic space, which we present as an infinite tree. And in this, on the symbolic space, we take p symbols. So each of those symbols is actually some path on the tree. And those, we can freely assume that those symbols are all different. Because we are going to integrate with respect to this probability distribution and this probability distribution of the event that two of those symbols are equal, of course, 0. Okay, so if we can freely assume that they are all different, then there exists, for each of them, there exists some times when it is different than all the previous. So what are those tau n that we are taking? For the first symbol, omega 1, we are taking the starting point. Let's say omega 1 is here. Sorry, omega. Okay. Then let's say omega 2. It is here. So what we will take? We will take the place where omega 2 becomes different than omega 1. There will be such place, because they are different. Then we have omega 3. For omega 3, we will take that place where omega 3 becomes different than both omega 1 and omega 2. It will be somewhere. And omega 4, we take that place where omega 4 becomes different than omega 1, omega 2, omega 3. It will be somewhere here. And so on. Okay, now what would be those vectors? Okay, this first was the very beginning. So this is where we have C1 plus Cp. So this will be the vector of which we calculate Fourier transform. Plus some rescaling. Those rescalings we'll take out. We will take into account later. Then from omega 2, this is the first place where we do not have omega 1, which means, but we have omega 2. So we will have C2 plus maybe some other guys, but for sure we won't have C1. Then omega 3, we take the first position when we do not have C1 and C2. So then we will have C3 plus maybe some other guys, but for sure not C1, not C2, and so on. So as you see, those guys are going to be independent vectors. In fact, the determinant of this matrix will be 1. Because this is 0 on the diagonal, we have 1 on the diagonal, and we have some things about the line. So this matrix has determinant 1. Those guys are independent. So what is going to be too bad? Just two sentences. What we are going to have is that this integral of theta hat is going to be just some number. But we will have those guys. That is, we have such choice of those cutting position, and this choice of the cutting position is, of course, not at one values of those omegas, but when we vary the values of the omegas, we can have the same position. That is, if omega 3 became different than omega 1 and omega 2 at this position, then we can change omega 3 on the old everything what follows, and it doesn't change this position. So we will have to write something like the sum of product of this lambda tau k and the integral of this d mu of omega 1 d mu of omega 2. And we need to prove that this thing is summary. That is finite. And when we can do this, which, okay, it would still take some 5, maybe 10 minutes, this will mean that the whole integral, okay, that this whole thing will become bounded. And then is the question of choosing gamma. It turns out that in order for this thing to be small, this gamma must be smaller than s minus 1. And then we need to choose p, which is even, but we need to choose it so large that p times gamma is larger than 1. And then we are getting the assumptions of the Kolmogorov theorem, and we can finish the whole argument. Oh, thank you.
Questions? Online?
May I ask a question?
Yeah?
Hi everyone. Michał, at the beginning of your talk, you mentioned that case when similarity dimension is less than 1, and, for example, greater than 1 is well studied. In first case, the Hausdorff dimension is equal to similarity dimension, but if similarity dimension is greater than one, then attractor contains open intervals. So you omitted case when the similarity dimension is equal to 1. Are there any piecemeal results related to this case?
Yes, there are. I think then what we know is that typically the dimension, the Hausdorff dimension of the set is 1, but the Hausdorff measure is 0. Except if we have open set condition, of course, because then we get the whole interval.
Thank you.
Some other questions? Thank the speaker.
I also have a question.
One more question.
Yes. So Michał, you stated your result for projections of natural measures, does it extend beyond it to other Bernoulli measures or possibly more general ergodic measures?
Yes. The only thing we need about the measure is that its local dimension is greater than 1 at every point in the symbolic space.
Mm-hmm. Okay, so some Bernoulli measures, for example, will
Yes, Bernoulli measure sufficiently close to the natural measure will also work, but the measure doesn't have to be Bernoulli. Basically, the only estimation is that the measure of the cylinder is is at most the size of the cylinder to power some 1 plus epsilon.
at every point, not at almost every point.
No, at every point, yes. Because if
At
you
every point.
that which is not true, then of course the density of the measure of the projection of this measure has cusp, so it cannot be held continuous. So this is kind of natural assumption.
And one more question. So your proof does produce some bounds on the Helder exponent that you get of the density.
Yes.
Do you have any expectations? What should be the optimal Helder exponent, or?
No, I don't have. That is, I would be very surprised if the method we are working here would be any close to optimal.
Okay, thanks.
Some more questions? No, so let's not see the speaker again.
Thank you. Goodbye. Goodbye. Goodbye.